Okay, to finish off about intermolecular forces, it's probably a good idea to talk about solubility. Okay, now there's a pretty good generalization, is that like dissolves or mixes with like. So what I mean by that is, right, let's think about water. Okay, water, and let's think about methane. Okay, which is I could make it that's methane. Could make it any alkane. Maybe if I'd chosen like octane C8H18, right? That is a liquid at room temperature, and we could see, will water and octane mix? Or I could think, can methane dissolve in water? And methane is just quicker to draw. Right, let's think about the intermolecular forces in water then. Remember, always go in this order. Think, first of all, can it do H bonds? And then if it can't do that, think, can it do dipole-dipole? And then if it can't do that, then it must be doing van der Waals. So I sort of always use that to think about things in that way. Right, water then. Lone pairs on the oxygen, very electronegative element. It's going to denude that. Yeah, so we've got the conditions there for being able to form hydrogen bonds. Water can form hydrogen bonds between itself. That delta positive water there can attracted to the lone pair on an oxygen. Okay, you get hydrogen bonds. Methane, well, carbon and hydrogen have approximately the same electronegativity. So that means there's no dipoles in that molecule. So there's certainly no H bonds. There's no dipole-dipole interactions. So it must be van der Waals forces. And the same would be true for octane. Now, if you try and mix octane and water, petrol and water, essentially, they won't mix. What happens is the water is heavier, that goes to the bottom, and the octane will form a layer on the top there. They're immiscible. And that is because they both form totally different sorts of intermolecular forces. If you imagine, if you put one of these big octane molecules in here, it would break hydrogen bonds, and you require energy to break bonds, and that's not going to happen. Or if you try to put water and you've got two octane molecules, and they're forming van der Waals forces, all these points of contact here. If you get a water molecule goes in between there, what's that going to do? It's going to disrupt all those. It's going to break van der Waals forces, and it requires energy to do that. That's not going to happen. So if you try and mix those two things together, they won't. Right, let's think about a few other things. Will ammonia and water mix? Let's have a think about ammonia and water. Well, ammonia is incredibly soluble. It's a gas. If you get a bottle of concentrated ammonia from the lab, it really smells. About 50% of that by mass is actually ammonia. 50% of the molecules there are ammonia, and 50% of them are water. It's really, really soluble. Why is that? Well, it is because ammonia has got lone pair on the nitrogen there, and of course that could form, and you've got these hydrogens are denuded. So there is, in pure ammonia, you can form hydrogen bonds. If you mix it with water, it can hydrogen bond to the water. So let's think there. That could go to the lone pair of water. So yeah, it is very, very soluble. No problem mixing them at all together. Let's think about ethanol. We know ethanol will mix with water. Otherwise, if you had beer and wine and things like that, it would have been two layers, wouldn't it? And it's not. It's all mixed up together. So ethanol and water. Here's ethanol. Why will that mix with water? Well, you've got a lone pair on the oxygen. You've got two lone pairs on the oxygen. You've got a denuded H plus there. Pure ethanol can form hydrogen bonds with itself. If you mix it with water, it can hydrogen bond to a water molecule there. So like dissolves like, yeah, they ethanol and water mixed together, no problem. Right, let's see what happens if you have a bigger alcohol. So here we've got a chain of just 2 carbons long. If I can make this chain a lot longer, okay, so let's say it's 8 long. Let's say we're going to make it octanol. So I will do 4, 5, 6, 7, 8. Okay, now if you try and mix octanol with water, it doesn't mix. I don't think heptanol will either. Now the reason why is because this end can form, that can form hydrogen bonds, can't it? This end with water. But if you think about the rest of this molecule, all that bit there, all you've got is CHs. So the predominant intermolecular forces, that is going to form are van der Waals. And because this is so much bigger than the little bit that can hydrogen bond with water, the predominant intermolecular force in octanol are van der Waals. That little OH is swamped by this big CH2 chain here. So the van der Waals are the predominant forces. Quite often, if you've got van der Waals in biology in particular, they'll call this bit hydrophobic. Okay, it won't form intermolecular forces with water because it can only form van der Waals forces really. And this end bit here you'd call hydrophilic because it likes water, because it can form intermolecular forces with the water. Okay, so that's always worth thinking about that when we're dealing with solubility. Just one more example, and if you ever use nail varnish, the smell of that is a chemical called propanone. I think I mentioned this before in an earlier video. Propanone, its trivial name is acetone. Right, now let's see what kind of intermolecular forces you can get there. Hydrogen bonds, well, you've got lone pair on the oxygen, but you can't form hydrogen bonds because all of the hydrogens are all attached to carbons. There's no hydrogen attached to an electronegative atom like oxygen. So there's no delta positive, there's no denuded protons to form interactions with the lone pair on the oxygens. So that can't form H bonds, but it can form. Can it form dipole-dipole? Well, it can, because that's going to be delta positive and that's delta negative. So you can form dipole-dipole interactions. Now the question is, will it mix with water? That will mix with water if you try it. And you might think, why? Well, although you can't have hydrogen bonds in the pure propanone, it can hydrogen bond to water because you've got a lone pair on that oxygen there. So what could be attracted to that is a hydrogen on a water molecule, which is a denuded proton, as we said. Okay, so that can so propanone, yeah, it will mix with water. And I think nail varnish remover is a mixture of water and propanone. I think pure propanone, if you get it on your fingers, it dries your skin out lots. It's not very nice. Pure propanone is very good for getting graffiti and biro off desks, and if you do that, you end up with sort of like white patches with dry skin. So I think nail varnish remover is a mixture of the two. Right, now before we finish about hydrogen bonds, I just want to talk about something you may have noticed from a bit of an anomalous bit of data. Well, initially it seems anomalous, but you may have noticed in the previous one with the boiling points of HF, H2O, and ammonia. All right, so we look at the boiling points here: HF, H2O, and NH3. Okay, so HF is 19 degrees, 19.5 degrees, the boiling point. Water is, of course, 100 degrees, and ammonia is minus 33 degrees. Now, what's going on there? Well, Well, if you ever think about the strength of the dipoles, which is the most electronegative element out of fluorine, oxygen? Well, it's fluorine, isn't it? So the dipole is biggest in the HF and then in the H2O and the NH3. So we're not getting a clear trend there because HF has got a, it's got a lower boiling point than water. If it was just the size of the dipole, we'd expect HF to have a higher boiling point than water, and it doesn't. Now, it's all down to the ratios of lone pairs to the denuded H's, okay? Right, if you think about HF, it's got, well, let's draw it here, HF. You've got 3 lone pairs per molecule, but you've only got 1 hydrogen, okay? So let's put that in there. 3 lone pairs, 1 H, like a hydrogen bond. H2O, well, water has got 2 lone pairs and 2 hydrogens. And ammonia has got, well, it's got 1 lone pair on the nitrogen and it's got 3 hydrogens, so it's the other way round to HF. So that has got 1 lone pair and 3 H's. So the problem with ammonia is you've got too many, okay? You've got too many hydrogens and not enough lone pairs. So you've got a shortage of lone pairs. If you think about HF, it's the other way around. You've got not enough hydrogens. You've got 3 lone pairs. Water, like Goldilocks and the porridge, just right. Yeah, it's got exactly the right number of lone pairs. Optimum ratio. So I think on average, if you think about the number of H bonds per molecule, on average, of course, not like individually, but water can form 4 H bonds per molecule, whereas HF can only form 2 because of that problem with the shortage of hydrogens, and ammonia can only form 2 as well. So when we look at that, this does explain the high boiling point of water because it can form a lot more hydrogen bonds than HF can on average, twice the number. And I suppose the other thing is explained, yeah, HF, yeah, they can form the same number of hydrogen bonds, 2 each, but the dipole is bigger in HF than it is in ammonia. So that's why the boiling point of HF is quite a bit higher than that of ammonia. Right, finally, I've got this picture from Wikipedia, and this is the author of the picture here. I've acknowledged it, right? So you've got a water molecule there, and you can see it's forming 4 hydrogen bonds. Okay, 1, 2, 3, 4. Okay, here it is it's the hydrogen forming a lone pair. There's a lone pair on this one. This hydrogen is forming a lone pair to that water molecule. And here, this hydrogen is forming a lone pair to the central water, and you've got the lone pair on the central water there. So 4 hydrogen bonds for that molecule. And of course, this is just showing one tiny bit of solid water, yeah, of an ice crystal. So you get this regular repeating pattern developing, and you can see that when you do a bit more on shapes of molecules, but this water is at the center of a tetrahedron. A bit like when you have methane, yeah, that's the carbon is at the center of a tetrahedron. Okay. So it's not a regular tetrahedron actually, but it's almost regular, but not quite. And so you get this regular pattern building up, and that's what ice crystals form. And if you're wondering why water, of course, it's got lower density when it's a solid, very unusually, than it has when it's a liquid, and it's due to the fact that these hydrogen bonds hold the water molecules slightly further apart when it's in this regular repeating pattern. Of course, when you've got liquid water, what's happening is these hydrogen bonds are continually breaking and swirling around and reforming and breaking and reforming, and so you don't get this regular pattern in liquid water. Anyway, I think we're just about done with intermolecular forces there, so we'll call that a day.